Oh, yeah, we're really good at 5 BCFTs, so that's going to be really easy.
Do they even exist?
No, I'm saying that it is literally, you can ignore literally two objects, but in flavor, there's something applies. I think it's safely assumed that we don't have a sort of like this compactification.
We should start and give Lara the opportunity to give her last short lecture today.
All right. So you guys are nearly through another week. This is awesome. You're in the home stretch, right? Quick recap from where I finished off yesterday. So what I've done so far in these lectures was tell you a little bit about SU3 structure manifolds, a little bit about constructions of Calabi-Yau's, and a bit about fibration structures, which play a huge role in string dualities, lots of string compactifications, and hopefully in proving that the set of such backgrounds in string theory is finite. This is still an open question, but there's progress and promise in that direction. So today what I want to do is actually stop talking about manifolds and start talking about other structures, specifically vector bundles on manifolds. And I'm going to use this as a way of probing different kinds of auxiliary geometric structures that we have to address. So this will also have some impact on higher form fields, gerbs, other things that you could be turning on in the geometry. Before I do that, though, let me just finish with 2 quick comments on manifolds. So I didn't have a chance yesterday to sort of summarize for you if you have this enormous number of fibrations in Calabi-Yau's. I mentioned that there could be, order thousands of different fibrations for one manifold. This has a huge impact on string dualities and a huge redundancy in the string landscape. So if you want to see a little bit more about examples in different dimensions of what you can do with these different fibrations in string dualities, this is a nice paper to look at that came out last summer. I should mention as well, there's even extremal examples. There's one manifold that we know of that actually has an infinite number of elliptic fibrations, which is kind of surprising. They get basically grouped together into a physically equivalent family, so it's not an infinite number of distinct vacua, but it's interesting that this can happen. Also, in everything I said yesterday, you might well ask, okay, so you've looked at all these data sets, you have a lot of evidence that there's all these vibrations. Basically, everything we know how to build is fibered, and you have a hope that this is going to prove to be true in general for Calabi-Yau's. But you might ask, could this be a feature of just we tend to build Calabi-Yau manifolds in the same way, right? We've been building things algebraically as hypersurfaces in Fano ambient spaces. Could it be that you're just looking under the lamppost, you're building something in a particular way, and they all have the same features? There is assorted evidence that this is not the case, and what we're seeing is actually more general about Calabi-Yau's. But for one specific example of that, a couple of years ago, my collaborators and I built a new data set of approximately 6,000 threefolds that were built in non-toric, non-Fano ambient spaces. These were a wildly different construction than what had been done for other threefolds, and we see all the same features. So all these guys are all fibered as well. Basically, all the bounds towards finiteness and vibration structures appear to be generic. So I don't have time to talk about this construction, but I just wanted to mention that it exists. There's also some evidence from other types of Calabi-Yau's constructed through non-abelian GLSMs, determinantal varieties, etc. Okay, so with that in hand, what do I want to do today? Today, I want to illustrate a danger, as I've done thus far, in just focusing on one piece of the compactification geometry in trying to analyze the physics. So somewhere in lecture 1, as I started off talking about SU3 structure manifolds, somebody raised their hand and they're like, hey, but don't you have more equations of motion that you aren't looking at? So basically, I've been looking this whole time from the point of view of the Strominger system at one spinor variation, which constrained the shape of the compact 6-dimensional space that I was playing with. Today, I want to come back and look at the rest of the equations of motion, the rest of EOM, and specifically those that constrain in heterotic, as an illustration, gauge fields. In heterotic, specifically, I'm interested in non-trivial gauge field vevs, A mu, on X, and what I can say about the properties, finiteness, moduli, and the way that these appear in the effective theory. That is the plan for the last lecture. So just briefly, let's remind ourselves what that last equation of motion looked like. So back to our various equations of motion, we ended up with a constraint on gauge fields, which to leading order looked like the following. We had a gamma mn, fa, where this guy's your gauge index, mn, where your 10D indices equals 0. This was written in real chords. And when you restrict this to the Calabi-Yau and you introduce, I should say this came from delta chi variations from my previous notes. When you restrict this to the Calabi-Yau, so on M6, and written in complex coordinates, the constraints on the gauge bundle take the following form. You have that the purely holomorphic and purely anti-holomorphic parts of the field strength have to vanish over the Calabi-Yau, and a contraction of your metric on the Calabi-Yau background, a B bar, with the 1, 1 part of the field strength has to vanish. Here, A, B are chords on X3. I'm going to be focusing on the case of gauge bundles over Calabi-Yaus. Actually, basically everything I say goes through to the general SE3 structure case. You get an equation that looks almost identical to this in the case of SE3 structure, still have a gauge bundle, still going to talk to the base manifold. But the Calabi-Yau is a little bit easier to discuss. So these have a name, these equations. These are referred to as the Hermitian-Yang-Mills equations. And to leading order, you've got to solve them. So you have to find a connection on the vector bundle, find an A that gives you an F that solves these equations over the Calabi-Yau. And if you have that, then that is a good background to begin your dimensional reduction. You can do an effective field theory. You can perturb around this background and work out the physics. Okay, problems. This is hard to solve. Why is it such a pain? Well, remember, we don't know the metric in any cases, right? So we do not explicitly know the form of GAB bar on the Calabi-Yau, which means that even solving the equation that we're trying to solve as a PDE for the connection is pretty impossible. Even in cases where you do know it, it's still a wickedly difficult PDE, and finding explicit solutions is a great big pain. But you need to do it. You need to do it in a big way. So this connection enters a bunch of stuff. Let me just give you a quick overview of where this enters the theory, and then we'll come back to how does one actually attack those equations. So what you need for physics about this gauge bundle. Quick overview. Some things you can work out pretty quickly, even if you don't know the solution. You know that the massless spectrum of the heterotic theory is determined by this bundle. This takes the form, just like we have the singlets associated to the manifold. These are counted by metric fluctuations. If you consider fluctuations delta A in the connection, this gives you the matter fields coming from the adjoint representation of the gauge field in 10 dimensions. Under dimensional reduction, these fluctuations give you charged matter fields, and these get counted by bundle-valued 1 forms on the manifold. So here, the notation, remember these are closed but not exact forms. 1 holomorphic index that lives over the Calabi-Yau, and then some other indices which are getting, which ones I'm interested in are being encoded by some representation of a vector bundle. I'll say what more I mean by that more explicitly in a second. But there are some gauge indices on this form as well, and those are encoded by the bundle. So you have to be able to count bundle-valued cohomology in order to work out your spectrum. Anomaly cancellation tells you, in the 10D theory, the Bianchi identity that you've seen already from me and from Vafa, this guy, F wedge F, trace R wedge R. This tells you that, in general, if you have a Calabi-Yau background, which I'm going to be interested in, so something where the H is trivial, or at least in the class of a trivial H, then it is not an option to turn off the field strength, right? So you might say, well, I just want to do a compactification. I don't want any gauge field vevs at all in my internal dimensions. There's two problems with that. First, if you begin with either the E8 cross E8 or SO32 heterotic string, if you don't turn on any gauge field vevs in the compact directions, you're only going to have E8 cross E8 or SO32 symmetry in 4 dimensions. That may not be so good. If you turn on vevs, you can break that symmetry down to any subgroup you like. And you can't satisfy anomalies because you've got a non-trivial contribution from the second Chern class, the R-wedge R term. So you've got to turn on some F. So we've got to include a non-trivial bundle, and then we have to say, what is it? Also, something that Professor Waffe mentioned, non-perturbative effects actually can be mixed and matched with the bundle. So specifically in the heterotic theory, in the language of normal heterotic language, NS5 branes are in the game. If I were doing heterotic M theory, these are M5s. And these can be sort of toggled back and forth between these and bundles through the notion of a small instanton transition in the heterotic theory. What's the idea there? Well, in the language of heterotic M theory, as Waffe described, you have an S1 mod Z2 orbifold, and you have an E8 symmetry, for example, on each of the fixed points of the S1 mod Z2, reducing M theory from 11 dimensions. And in principle, you can have 5 branes in the bulk, branes, and you can choose to move these 5 branes onto the fixed points of the interval or off, right? So they can be either in the internal part of the interval or they can hit the endpoint. If they hit the endpoints, they can be absorbed into your definition of the bundle, or you can choose to split off a piece of the bundle and shove it into the interval, and that will turn it back into 5 brane. So basically, the notion of 5 brane and bundle is all kind of, you can flow back and forth between the two. And this actually matters for the anomaly cancellation. So if we say the class of DH is 0, what this tells us is that the second Chern class of the holomorphic tangent bundle has to be the second Chern class of my vector bundle V plus the class of an effective curve inside the Calabi-Yau that is wrapped by the 5 brane. And you can choose, if you choose this to be trivial as instanton number, you can absorb that into the C2, or you can pull it out as 5 brane, vice versa. It doesn't change the fact that DH is 0. So although Professor Waffe was saying the 5 brane source H, this is true, this is all trivial H in the sense that it's not quantized. So you can shuffle it back and forth. It is essentially cohomologically trivial. In the case of SU3 structure, you have H that you just can't turn off ever. So you still have branes and bundle in play. OK, so you care about what the bundle is doing and how it behaves because of small instantons. Also, just continuing this list, couplings. For example, holomorphic Yukawa couplings in the superpotential. These are formed by cup products of one forms, things that look like H1XV. I'm not going to go into detail with what this is, but just these are things that you can compute. We have the technology to do all this. This is a so-called Yoneda product. So if you give me a basis of one forms that are bundle valued over the manifold, I can count the 0-mode spectrum. I can work out the couplings. Also, A mu enters in a big way the matter field Kähler potential in the n=1 theory. So the normalization of fields, if you want to talk about masses of fields in your 4D theory, this is really important. It also enters into, actually, by restricting gauge fields to rational curves, this also enters into instanton effects, contributions to W, etc. So there's a big long list. So basically, if you want to calculate the full form of your matter spectrum, your masses, your potential in 4D, you have to have really explicit computational control over these gauge fields in order to be able to work out all the details you want to work out. So not only do we have to know about bundles, not only do we have to know about manifolds, we also have to know about bundles over them. Let me just say a quick word about what a bundle is. This is the the 2-cent cartoon version. Probably everybody knows this already, but if you're talking about gauge field vevs, this has to do with the notion of a bundle. Mathematically, a bundle is extremely similar to what we just described with vibrations in previous lectures. So bundles, you have a map which takes a total space of a bundle, I'll write it as V, onto the base, X. So over our Calabi-Yau, this is X, the Calabi-Yau. We have so-called fibers. And the only difference between the fibration that we talked about already and a bundle is that in the case of the fibration, you only have this homotopy lifting property where the fibers have to be the same for generic fibers. So you say if I pick a generic point and another generic point, the fiber better look the same. For a bundle, every point has to look the same. So you're not allowed to degenerate anywhere. So it's a fibration with no degenerations, basically. So a classic example, of course, let's do U1 gauge theory. Then the fibers are your gauge degree of freedom. This is one complex number at each point in your space, e to the I phi. And that phase that you keep track of at every point in space can be fibered in a non-trivial way over a given base manifold. So going back to 2 analogies I gave you before, cylinder versus Mobius, these are the only U1 gauge fields on S1. If you say, I want to do U1 gauge theory on a circle, how can I do it? The 2 ways that you can keep track of the phase of electromagnetism is either trivial, that's the cylinder, or you can have one twist as you go around. That's the Mobius strip. OK, so there is a geometry to the total space, just like there's a geometry to the fibration. Here, the fibers, unlike what we were describing with fibers in Calabi-Yau's, there the fiber is compact. Here it is non-compact in general. So the fiber is whatever space you want it to be. We're interested in vector bundles in heterotic because we are talking about gauge symmetry that we're keeping track of at every point, and that forms the vector space. OK, so with that in hand, we know that we need to solve Hermitian-Yang-Mills equations. How are we going to do that? Well, let's look at the easy, quote, easy one first. This guy. This one is easy. Why do I say that? What this one is telling us, FAB is F A bar B bar is 0. This guy is actually telling you that your vector bundle, V, is, quote, holomorphic as a bundle. And you can prove that those field strengths will vanish if, as you move from patch to patch of the manifold, the transition functions that tell you about how the bundle changes, the TIJs, are holomorphic functions. So the TIJs are equal to TIJ function of Z only, not Z bar. So that's just a simple statement about how you're building the bundle. If you have holomorphic transition functions, then you're good. So I'm halfway there. I just have to worry about the other half. So TAB bar, FAB bar equals 0. This is a big pain, and again, we have Yau to thank for simplifying this for us. So just like Yau's theorem for Calabi-Yau metrics told us that there was a simple property, namely the first Chern class of a Kähler manifold, that we could check that guaranteed the existence of a metric, Yau came up with a nice property that guarantees the existence of a connection that solves this guy. So this is a theorem due to Donaldson, Uhlenbeck, and Yau. Historical note, Donaldson worked by himself, Uhlenbeck and Yau worked together on this. And what they proved is that the solution to this equation is one-to-one with a property in algebraic geometry known as V is a, quote, stable bundle. I am not going to give you the technical definition of stability today. It's fun to play with, but we don't have time for it. Here's the intuitive version. Stability, very intuitively, constrains sub-objects. So let's have a U inside V. It basically limits possible U's. So very intuitively, what it's saying is V is as irreducible as possible. I'm having to make this more precise later for anybody who's interested. But the basic idea, think about it like building blocks. So you have a bundle that could be built out of stuff. And what you're demanding with stability is that you want it to be built out of the minimum number of ingredients as possible, and there's no natural way to sort of pull it apart into substructure. This matters a lot because basically you can use stable bundles as building blocks. So stable bundles are the building blocks of all bundles. So you can combine these general gauge configurations, let's say. Mu configurations. So if you're writing down some general object, you can always find a decomposition in terms of stable subobjects. Okay. As it frequently happens in life, Yao says, well, if you can understand the algebraic geometry substructure, at the level of algebraic geometry, this just says, find for me all objects U that have a non-trivial morphism that injects them into V. If you can work out that, then you know you have a solution to the differential geometry problem of Hermitian-Yang-Mills. Unfortunately, there is conservation of misery in life, because that is a wicked, hard PDE to solve, and it turns out that actually finding vector bundle substructure is also a pain in the butt. So this is still hard. Still hard, but not as bad. But sometimes doable. So at least it's progress. Okay. So we're not going to go into the details of how we prove that, but what I do want to do is say what is known about how to classify stable objects. And then we're going to look at the physics of how these things actually change the geometry of their base manifolds and also the effective physics that I need to solve. So first pass, we're now up against another classification problem. So we know that we have to ask how many different base manifolds X, so number of X is a question. Now we want to know how many V on X stable do we have for each Calabi-Yau manifold, right? If we have an infinite number of those, once again, we're going to have a problem that we have to somehow characterize an infinite number of effective theories. Okay, so to do that, we have to know what do we mean by different vector bundles. There's a projection map. So different vector bundles, the first thing is that there is a moduli space, curly M of V, which is fixed by the following data. I need to tell you the structure group, G of my bundle. This is related to also the rank of the bundle, so what dimension the fiber spaces are. And over a Calabi-Yau threefold, write it this way, I have to tell you about the Chern classes. These are exactly as I defined them for the tangent bundle. So for C1 of X, this was just trace of the curvature. C1 of V is trace of F. And all the appropriate higher bilinears, trilinears, etc. Okay, so in order to tell you about whether there's a moduli space of bundles that is trivial or not, whether a bundle exists, whether there's an infinite number, we have to decide what rank and structure group we're allowed and what bounds the topologies are not. Just like the Hodge numbers of the Calabi-Yaus could be infinite, if the topology of the bundle is completely unconstrained, then there's definitely an infinite number of things we could have. So what do we know about that? So first, the rule is that since we start with, for example, E8 cross E8 in 10D, if this is my group, actually, let me just call this E8 cross E8. If I have a G bundle, what I'm looking for is a product structure, G cross H, inside, say, a single E8 factor. If G is the bundle, this guy is associated to V, this will be my 4D gauge symmetry. This is nothing deep. I'm just saying if you turn on a VEV in a subgroup of E8 that's valued in G, the commutant of G inside EH is everything that's unbroken, right? Everything that commutes with this is what you get left over in 4D. So depending on what I choose here, different G's, I will get different effective theories. So just as an example, if I choose SU5 inside E8, as my G. This leads to SU5, gut theory, and 40. You can ask if you have SU6, that can actually give you standard model symmetry of SU3, SU2, U1, etc. So choosing different bundles will give you different allowed symmetry. So what am I constrained by? I'm constrained by G's that fit inside of E8. So the structure group has to be a subgroup of E8. That means the maximal rank that I can have is 8. So rank of V had better be less than 8. Other constraints, C1 of V has to be 0, actually strictly 0 mod 2. This is the vanishing of the Stiefel-Whitney class. This is spinors. So spinors in the 4D theory are not just valued in the tangent bundle of the space, they also talk to the gauge fields. So in order to have spinors, I need C1 equals 0. Just being a little bit precise, you could say, is it C1 equals 0 or C1 equals 0 mod 2? It turns out all the generators of E8 are traceless, so this actually has to be strictly 0. If you have a reducible bundle, the pieces could be non-zero, but they have to still sum to 0 inside the total bundle. We've already talked about constraints on C2. So C2 of V, we know, has to be less than or equal to C2 of the holomorphic tangent bundle because of this guy. Where did I do? Here we go. So here, I know that I need to balance this possibly with non-perturbative effects against C2 of the tangent bundle. I could have a non-trivial effective curve class that the fibranes are wrapping. If I have fibranes, I don't need these guys to be exactly equal, but I do have a bound on the C2 of my bundle from above. Okay, C3, you can prove that in the heterotic theory, this is related to the chiral index, i.e. this is the number of generations minus number of anti-generations in your 4D theory. So if, for example, you were interested in building the standard model, you would want this to be 3, right? 3 families of quarks and leptons, no anti-families. But there's no physical constraint that tells me that C3 has to be anything in particular, right? In principle, I could have an infinite number of generations. So the only ones that I have firm bounds on are C1 and C2. However, so in terms of the representation, so just as an example, suppose I was talking about SU3 as my 4D theory. This is the number of 3's minus 3 bars. So conjugate representations. Okay. So physically, we've got a bound on C1 and C2 and the rank. Yep.
So I thought that in a heterotic case, the number of families
Great question. So that is true only in one class of heterotic compactifications. If you have the so-called standard embedding, where you choose, so 1 e.g., suppose that I took A mu equals to omega spin, i.e. V is equal to Tx. This is actually something I should mention, so this is a great point. If you choose V equal to the holomorphic tangent bundle, i.e. the SU3 bundle, that always embeds in E8. This always exactly satisfies this, because here these guys are literally equal. So you have a strictly Calabi-Yau, definitely 0 solution. This will always lead in 4 dimensions to an E6 theory. Right, the commuton of SU3 inside E8 is E6. So you can do that. In this case, what you said is exactly right. Then the Euler number of the Calabi-Yau is the index, the chiral index of the theory. If you choose any other bundle, then the Euler number of the manifold doesn't matter. It's the C3 of the V. But this is a great one to point out because when people were first writing down heterotic theories, this was the very first solution they wrote down. So they said, hey, I can always do that one. So this guarantees for every Calabi-Yau, you do have a good full heterotic compactification because you can always make this choice. Any other questions? Okay. Good. So far, so good. So we need to try and say, can we further bound topology? And there's a cool result due to mathematicians Maruyama and Langer, who proved the following. For V stable, i.e. satisfying the equations of motion we care about, if C1 and C2 fixed, then there exists a finite number of possible, i.e. compatible, C3V values. So the topology does not get to completely get away from you. You may not know what it is, but if you hand me a Calabi-Yau, if you tell me what the C2 is of the Calabi-Yau, then I have the C2 of my bundle. If you tell me what that is, there's only a finite number of chiral indices that can exist for that 4D theory. Unfortunately, Maruyama and Langer do not actually enumerate what that bound is, how big the chiral index can be, but we know that one exists. So there is, in fact, a finite number of topologies that could be available for any given heterotic compactification once you fix the base manifold. So you tell me the base manifold, and then say, how many gauge fields can I write down? For topology, there's finite. You might say, like, well, what about total number of bundles? There are also results, so with some caveats to do with which structure groups we're considering. It is known there exists a finite number of stable bundles, i.e. a finite number of disjoint components of the bundle moduli space with fixed topology. So we're relatively on top of finiteness. The gauge fields don't get to be completely run away from us. If you tell me what the base manifolds is, if we could, for example, prove that all Calabi-Yaus are finite, then we can start constraining the bundles over them. Okay, so far so good. Now the question is, well, a question. What about moduli? So remember, we did this calculation, or sketched this calculation for the Calabi-Yaus. We let the metric fluctuate. G goes to G plus delta G. And then you say that the Kähler and complex structure moduli of the Calabi-Yau, those are your degrees of freedom in the geometry, which characterize a lot of things, right? The Hodge numbers play a lot of role. They give you massless scalars, and they do other interesting things for you. So here, we want to let A go to A plus delta A and ask, what is the structure we get? You can show that from this equation that the basic constraint is that d bar of delta A is 0. And if you look at how what representation of your gauge field A is always in the adjoint. So this actually tells you that the guys you're interested in are d bar closed, one forms, because A has one index living over the Calabi-Yau, that is valued in bundle language in the traceless endomorphisms of the vector bundle, i.e. this is just saying adjoint rep of G. So there is a bundle-valued cohomology that you can calculate that will give you the number of moduli associated to your bundle, just like you could calculate the Hodge numbers for the Calabi-Yau. And just like Hodge numbers for a Calabi-Yau can order in the hundreds, so can this. So actually, you have a big moduli problem. The singlets in a heterotic theory are H11 of X, H21 of X, plus H1 and 0V. Naively. I will come back to whether this is actually true in a minute. Question mark, but naively you would expect a lot of stuff. Another comment, the analysis that is normally done, that was done for the complex structure and the Kähler moduli of the Calabi-Yau, and that's being done here, is a first-order deformation theory. So you just say, I fluctuate, I keep only the linear contribution. What do I get? You could ask what happens, this is what you get for first-order deformations. You could ask what happens to higher orders. So there's actually some nice proofs. Let me write this down. So deformations, if you look at, for example, H1Tx, which is H21 of X, you can say that this space parameterizes the first-order deformation space of the complex structure. What happens if you wiggle further, right? If you wiggle further, could you have a higher-order obstruction? So could there be a non-trivial potential in this theory that actually lifts those degrees of freedom if you look beyond linear order? This is proved in the negative for Calabi-Yau. So here, these are all unobstructed. Unobstructed. So the claim is that the first order result is actually true to all orders. No matter how high you fluctuate, you will not lift any further degrees of freedom. This has to do with the fact that n equals 2 theories do not have a superpotential. So in type 2a and type 2b, right, you're not going to change the number of complex structure moduli. This was proven by Tian for complex structure moduli, and you can use mirror symmetry to argue that the Kähler moduli are also unobstructed. However, important to note, this H1N0V, the bundle moduli, is first order only. So this can actually be lifted to higher orders in deformation theory. Just at the level of math, if you wiggle it, there can be higher order things that lift these guys. And that's a statement that the superpotential in the n equals 1 theory is in general a function of all the moduli. So you can have higher order lifting, higher order mass terms that arise in the superpotential for these singlets. That'll matter to us in just a moment. Okay, so I said that this counting, I put a question mark here. So the question is this really a direct sum of moduli like this? Is it fair to say that the bundle is just kind of sitting on the manifold, it's doing its own thing, they don't talk to each other? Is the existence of a solution sort of modular like this, that I find a good bundle, I find a good manifold, I put them together, and that satisfies everything? So the naive thought, this guy was sort of naive belief from the 1980s up until fairly recently. People working in heterotic compactifications just assumed that that decomposition was in fact true. However, it is not, as it turns out. So basically the question that I want to address now is, do V and X constrain each other, both in terms of their moduli and in terms of whether we actually have a good solution to our theory? I am illustrating this for a bundle on a manifold, but I should say that this exact same analysis can be done for n-form flux, n-form flux on X. So you can ask this question. I'm asking it about a gauge field, basically. You can ask it about a 2-form, a 3-form background, any flux backgrounds in type 2 theories, M theory, et cetera. You can say, again, how does this background affect the base manifold? So to do that, we need to actually, to answer how this works in heterotic, we need to go back to the equations of motion. So back to the equations of motion. So the first question is, all right, these are my guys. Where are various degrees of freedom entering these equations? So clearly, delta A fluctuations will change the F portion of any of these equations, right? Also, I have a 1-1 metric here. Obviously, Kähler moduli will enter through the metric. But even the way I've written this depends on the complex structure in a big way, right? I wrote this in terms of complex coordinates. So if I change what I mean by complex coordinates, can I actually change whether these equations are satisfied or not? The answer is yes, actually. So all of this depends on all moduli. And this matters to us because if we fluctuate the three things we would want to fluctuate, well, there's the delta G, which breaks into complex structure or Kähler structure, and the delta A that we've just discussed. If I consider an arbitrary fluctuation where I let all three of these things change at once, I want to know what is the true moduli space of this theory? What is the true object that's parameterizing deformations? Because if I can vary in one of these directions and screw up these equations, that must mean something about both the validity of my solution and the effective physics in my low energy theory. So what I want to ask about is a total moduli space of the heterotic theory. I should say that actually to do this fully properly, I should also add in a delta H, non-trivial. In the Calabi-Yau case, I can choose to freeze this. In the Strominger system, you have to turn it back on. And this has actually been done for the Strominger system as well, so I'll talk about that in just a moment. But let me illustrate with delta H turned off for now. OK, so to see this, let's actually illustrate what this is doing in the 4D theory first, and then we'll talk about how to solve it mathematically. So to see what this looks like, let's start in 10D. And I want to show you a piece of the 10D action, partial. So there's a piece that looks like trace f squared minus trace r squared integrated over M10. This is just one piece of a bunch of terms from the bosonic action that I wrote before. No, it's not the leading order term in the curvature. There's a Ricci, an Einstein-Hilbert term leading order. This is the curvature squared term. And remember, we have the Bianchi identity. DH is trace f wedge f minus trace r wedge r. Now, if I wedge this expression, this is over the Calabi-Yau that I'm going to be interested in this. If I look at restricting this to the Calabi-Yau and wedging together with the Kähler form, what I have is that over x, if J is my Kähler form, I know that this has to be 0, r wedge r. This is just a true and boring statement. So using this expression, plus the fact that x is Ricci flat and Kähler, it turns out that you can show that if you were to expand out all of these guys in terms of the indices, whether they're running over the 4D or the 10D part of your space, you can show that this implies the following. M10 minus G trace f squared r squared plus 2 a bar b bar squared f a b a bar b bar a e b is 0. Where here, I'm not showing you the algebra, but you can literally just write this out, keeping track of all holomorphic, anti-holomorphic indices, and you can show that this must be true. So what this tells me is that there is a piece I can replace this part, plus a lot of other stuff. I can replace this part of my 10D action with something that explicitly involves the equations of motion over the Calabi-Yau. So the punchline is the following. So if I substitute sub into S partial, what I am left with is the following. Partial goes like M10 minus G, and then this piece that looks like my equations of motion. GA B bar plus AB A bar B bar GA A bar B B bar plus stuff. All right, why did I bother to write this all out for you? The nice part about this is thinking about this just as a piece of the 10D theory. You can see manifestly that this does not depend on 4D derivatives, i.e. there are no 4D derivative terms in this expression. So whatever this is, when I dimensionally reduce down to 4D, this is a part of the 4D potential in terms of the 4D matter fields. So I have a non-trivial contribution to the four-dimensional potential. If I start with a solution to my equations of motion and I fluctuate any degree of freedom that screws up these equations of motion, then I will generate a non-trivial potential in the 4D theory that's going to push me back towards the vacuum, which makes sense. So it is clear 4D potential So whatever these conditions are, coming back up here, where did I write them? Yeah, here, in terms of the n equals 1 theory, basically the obstructions to moduli that I could have from either this guy or this guy must be parts of the 4D theory. There must be potential terms in the 4D theory associated to each of these possible terms. Now, we know a lot about the structure of potentials in n equals 1 theories. It is not a big stretch to say that what I have as my ingredients are D term or F term potentials. So it better be possible to rephrase those two conditions as D or F terms. And that's what I want to show you schematically, is how you do that. And then also how you see what the true moduli space, both of the physical theory is and of the geometry. So clearly, potential will obstruct delta G, delta A that violate the equations of motion. That is not a deep surprise. But what I want to start with is how to see this explicitly. So let's start with the easy guy. Let's start with the holomorphic condition. So I said this had a simple geometric interpretation. The transition functions are just holomorphic functions. I have a, quote, holomorphic bundle. But the question is, if I give you a complex structure on the base manifold, and I start fluctuating that, does a holomorphic bundle stay holomorphic? Or can it get away from you? That's what we want to investigate. So this clearly depends on the complex structure of the manifold, the way I've written it. So in order to talk about these fluctuations a bit more precisely, let me try and write this in a way that doesn't depend on those complex coordinates quite so manifestly. So let's look at this guy in a way that we can track the variations of the complex structure. So let me introduce projection operators. Now let me define in terms of real coordinates, Pij, 1 plus I complex structure, Ij. This is the complex structure tensor that squares to -1. And its conjugate, Ji, which is identity Ij minus Ij, Ji, where again, J squared is -1 is complex structure. So the reason this is a nice writing in terms of projection operators is if I vary what I mean by the complex structure. So if I let J go to J plus delta J, here this is 2-index guy, Ij, then I can manifestly see that change through projection operators. And if I do that, my equations of motion can be written in terms of these projection operators as Gij, Pki, P bar Lj, Fkl is 0, and the other two guys are these Lk, Jl, and double barred Ij, Lk, Fjl. So I'm just making explicit in my equations of motion what the dependence on complex structure is in these equations. So now if I vary J and I vary A, I know how to see the variation of A in the field strength, and I know how to see the variation of the complex structure in these projection operators. And I want to consider the perturbation. So as I wrote here, this is one thing, and I want to also consider A goes to A naught plus delta A. And I want to ask, what is the equation that I must solve if I allow these guys to all vary and demand that I still get a solution? What is the leading order constraint on delta J and delta A. I'm not going to do the algebra in the interest of time, but I'm just going to show you the answer. And here, so it turns out that the only non-vanishing fluctuation delta J, in terms of now rewriting this in terms of complex coordinates, B bar A, can be written as minus I some coefficient delta Zi expanded in a basis B bar I B bar A, where this is a basis of two one-forms. So you say, how can the complex structure fluctuate? It's some set of coefficients that are arbitrary, expanded in the basis of two one-forms on your manifold. And so with this in hand, what you can show is that the equations of motion give you the following constraint. Have that dzi, vi, c, a bar, f0, c, b bar, plus the background d, a bar, delta a, b bar is 0. So let's look at what this equation is saying for just a second. So naively, what I thought of as complex structure was these guys. And the fact that these were d-bar closed, this was enough to be a good variation of complex structure for the manifold by itself. If I had no variation of the manifold, so if I don't vary the complex structure, then this is just the condition to be bundle moduli. You have a fluctuation of A that is d-bar closed. So if either of these terms existed by themselves, you would just have a fluctuation of complex structure or a fluctuation of bundle moduli. But what this is saying is that the true answer is actually neither of those equations. It's not H21 or the bundle moduli. I have to solve this guy. I have to solve a balancing of these two. So the two intuitive pieces, I need my field strength to be of 1,1 type. So this is a fluctuation of complex structure that rotates the 1,1 field strength into a new direction, a 0,2 direction. And this is a delta A that is not d-bar closed, which is also turning on a non-trivial F02. Okay, so punchline here, not every fluctuation delta Zi in complex structure can be balanced by a delta A. So this means that this naive sum of the moduli that I thought I was writing down is not correct. In fact, the presence of the bundle, V can, quote, lift moduli of X. You might say, why am I saying it that way around? Couldn't the moduli of the manifold lift degrees of freedom from the bundle? I'll show you in just a second. It turns out this is actually asymmetric. So it is actually true that the constraint falls on the delta Zs. So you can show that this is asymmetric in the sense that there will be delta A's that exist to compensate for some of these guys. And any delta A that is d-bar closed is actually automatically a good solution. I'll show you more about that in a second. But the punchline is, now your geometry, the pieces of your geometry are talking to each other. So you don't just have a manifold that has some degrees of freedom and you stick a gauge field on it. The gauge field is freezing degrees of freedom in the base geometry. And you care about what that looks like, both from the point of view of moduli stabilization and also the fact that those Calabi-Yau moduli enter into a ton of pieces of your effective theory. So they enter into quark masses. They enter into coupling constants. Whether you are at a good or bad point in moduli space phenomenologically now really matters. Where did the bundle force you to go? Okay, so the question is, if the moduli space wasn't the direct sum that I wrote down before, what is it? What is the true moduli space? And can I calculate its dimension? Any questions so far? Since that was kind of technical. Yeah.
My normal information I have full
Mm-hmm. This is an n equals 1 theory. There is no R symmetry. Yeah. Yeah, no, I mean, in 4D, it's just, you don't, so this whole structure that, for example, the Calabi-Yau degrees of freedom are protected by themselves, I mean, that's a deeply n equals 2 statement. And as soon as you start adding other ingredients, fluxes, anything else, then, yeah. Yep, no, n equals 1 at the moment. Okay, so to find the true moduli space, let me first address this in math, and then I'm going to tell you what it looks like in field theory. So to do this properly, we need deformation theory in mathematics, which is, just like it says on the tin, you start with some geometric object, you wiggle it, and then you say what is allowed for those wiggles. So there are three objects in deformation theory that are in play here. There is a deformation space of X itself. This is the variations or the deformations of X as a complex manifold, namely the variations of its complex structure. And as we've already described, this is H1Tx, which for a Calabi-Yau is H21. I should point out that for any manifold, actually not even Kähler, any Hermitian manifold, the complex structure always lives in H1Tx. The fact that this happens to be equal to the Hodge number H21 is a Calabi-Yau fluke. There is also the deformation space associated to V, and these are defs of V over X, i.e. delta A's, changes in connection, for a fixed complex structure of X. So if you freeze the complex structure of the base manifold and just ask how the connection can vary, what you find is that to leading order, that's this guy that I've already introduced for you, H0 N0V. So what we call the bundle moduli are a well-defined geometric object. They are the fluctuations of a connection while you hold the base geometry fixed. But of course, in physics, you're not allowed to just freeze degrees of freedom by hand. So neither of these is actually the right deformation space to do physics with. You need a combined deformation space. Unfortunately, this does actually exist in mathematics. You need the deformation space of the pair, X and V, which are, as you would imagine, all possible changes. Here I'm illustrating complex and delta A fluctuations. You can also put Kähler fluctuations into the mix, but let me not go there just for the moment. Deformation space of this guy, which are defs of V over X, which vary delta J, Ij, and delta A simultaneously. And this has a nice geometric interpretation as well. So let me put that up, bring this down. So what are you actually changing geometrically in this picture? Remember that complex structure is just wiggling the shape of the complex manifold. So using the quintic as an example, changing the complex structure is just taking one quintic polynomial and wiggling it to one nearby, a different polynomial defining equation. What are we doing for this combined deformation space of a bundle over its space? What you actually want to do is consider V over X as a complex manifold. Now, the fibers are non-compact because they have, these are SUN fibers, for example. But you can make it a compact manifold just as we did before. Remember when we started with CN and went to projective spaces to build Calabi-Yaus? You can projectivize the fiber directions to make the total space, so this is a compactification of total space of V. Okay, so what is that? Think about the bundle just as geometry, right? I gave you the Mobius strip and the cylinder example. The fibers, which are your gauge symmetry at each point, these are just a physical direction that you can view as part of the geometry. If you cap off the overall scale of those fibers to make it into a compact manifold, now you just have a big compact manifold that is describing all your gauge fields and your base manifold all at once. And this guy has, let's call this curly P for the total space here, the complex structure moduli of curly P, H1P, these will be the complex structure moduli of the total object. So that's an easy thing geometrically to see, but now the question is, how do I break it into the parts, right? I want to see what's left. And it turns out, thanks to ATIA, there's a nice decomposition of this H1P into pieces that live over the manifold. So the answer is that you have structure like so. And the true moduli can be written as H1Q. So there is some bundle-valued cohomology on X. I should write here. Sorry, if you haven't seen this notation before, one forms that are closed but not exact. X tells you which space you're on. Q tells you the form type indices, the gauge field indices on the form. OK, what did I just write here? So I got weird arrows and some objects. What this is saying is that Q, the moduli that are actually in your theory, are not either the bundle moduli. Let me actually write this slightly differently. Sorry. Keep my notation same. M0V, traceless endomorphisms of your bundle. They're not either the bundle moduli or the complex structure. They're a non-trivial mixing. So let me define this notation just briefly. Quick aside, this is super useful. When you see these arrows in various mappy places, this is known as a short exact sequence, which is pretty much the most useful thing in algebraic geometry. What is the definition of a short exact sequence? If I have a bunch of maps, which is what the arrows represent, then a sequence is called a short exact sequence if the kernel of a given map, Fn plus 1, is equal to the image of the map that preceded it. OK, why am I telling you this? Because for a short exact sequence, one that has exactly 3 terms, you can have more terms and that's still an exact sequence. The short here means that I have 3 different bundles that are getting mapped into each other. What this means is that this map structure has a really nice feature, which is that it's a way to quantify what you mean by almost a sum, or how you glue things together non-trivially. So if you look at the structure of these maps, if the kernel of one map has to be the image of the one in front of it, this tells you that the map F2 is injective, i.e. A is a subset, a subspace, or a subbundle of B. So it's saying whatever bundle appeared first in that sequence, it gets embedded in the middle one. And likewise, it tells you that the map F3 is surjective, because if you look here, again, kernel image, saying the kernel of this guy is the image of the previous one, because there's a 0, you're good. Here, the kernel of this guy is the image, or this one. The kernel of this one is the image of the previous one, so this guy has to be surjective, because clearly the kernel is everything at that stage. So here, surjective, and that tells you that C can be written as a formal quotient of whatever is in B that isn't A. So what this means is that B is, quote, almost A plus C, the direct sum of 2 bundles. But the almost here means not quite. The non-triviality of those maps that map between them means that the connection i.e. A sub B, A mu on B, the gauge connection on the bundle B has the form of A that came from A, an A that came from C, and it's almost block diagonal. However, there's a non-trivial piece up here. I'm going to give it a name and call it x1. There's a non-trivial off-diagonal component in the connection that glues together A plus C. So it is literally a non-trivial gluing of your two bundles into something indecomposable. So why am I wasting my time with this? Let me just say, in the case of bundles, sorry, one last comment, and then I'll explain why we're doing this. Formally, the X group, which some of you might have seen before if you've taken math classes, but if you haven't, don't worry about it. This non-trivial gluing, in the case of bundles, is just an explicit bundle-valued cohomology again. This is H1 of A tensor, the dual of C. So short exact sequences of this type are the workhorses of algebraic geometry. Why am I telling you that in this context? Because the true moduli of the heterotic theory, the true gauge bundle that's actually determining the moduli space, is not where the adjoint gauge fields live. It's not where the holomorphic tangent bundle of the manifold lives. The two have been non-trivially glued together into an object that I'm calling Q, and it is the moduli of Q that are the moduli, the true moduli of a heterotic theory. And you might say, this is just a bunch of math. Why did we do this? Once you can quantify what geometric object it is you want to count, you are in business. So now you actually have the capacity to go away and calculate a number. You can find the degrees of freedom in your theory. And in general, this number is very different than what you might have naively calculated if you just added up all the pieces independently. Yep. No. It is the restriction of the tangent bundle to the total space to the base. That helps. So yeah, holomorphic tangent bundle to the projectivized total space restricted to the base manifold. Okay, so final statement. I am really running short on time, so I'm just going to have to give you the punchline. So what you can show by analyzing the cohomology is that H1Q is equal to H1 of N0V, the bundle moduli that you had in the game to start with, plus a piece of the complex structure moduli of the base. I'm going to call it the kernel of a map alpha, where alpha maps H1TX, the complex structure, into H2 of the traceless endomorphisms of V. And this, in general, Ker alpha is generically less than equal to H21 of the manifold. And a question is, if I just pick a random bundle out of a hat and I bung it on a Calabi-Yau, how much less complex structure do I get? So you can start simple. You can start with a billion gauge fields. So this is a line bundle L over X, for example. So U1s, if you have a U1 gauge field, you can prove that this actually fixes no moduli of its base. For U1s, you have a naive moduli space was correct. You have H1 and 0V plus the full H21. You don't fix anything. Then you can work your way up and you can say, well, okay, a billion's pretty easy. What about the simplest non-abelian gauge fields I'm allowed to turn on? So you can say, what about SU2? And you can say, what generically happens? And the answer is here that Ker alpha is considerably less than H21. Namely, you fix almost all. So if you pick a bundle out of a hat, you will reduce the moduli space from hundreds down to tens or ones for the simplest SU2 bundles you can write down. So this moduli space, this was not a small effect. As soon as you move away from billion gauge fields, you freeze basically all of the complex structure moduli of your base. Now, I should say, why should I say basically all? You can say, what's the best that you could do? Because you're kind of interested in rigid objects for Pheno. How far can you push this? The best that I have personally been able to construct with bundles, again, using pretty low-rank simple bundles, you can fix all but one complex structure modulus this way. So coming back to Vafa's lecture about, is there a fully stabilized vacuum? We know that stabilizing, for example, the dilaton or overall volume in the Kähler moduli is difficult. Maybe there's some sort of n=1 mirror symmetry going on. So far, we have not been able to fix all of the complex structure of the base manifold this way. Maybe we just don't know what we're searching for yet. So we don't have a proof that you can't make the base entirely rigid this way. But so far, the best you can do is one left over. All right. I went slower than I anticipated. So why do we want to know this? What are the things that I want you to see? I was going to show you the effective theory where you can get this same lifting, which will be in my notes. It's actually a fun analysis, but you can show that this effect in the 4D theory corresponds to an F-term lifting of moduli I should be a little careful when I say F-term lifting. Generically, the scale of this F-term is, for most points in moduli space, actually the scale of the compactification. So the things that you were removing from the theory you should never have counted in the first place. So here, you just didn't have as many moduli naively as you thought you did. Though at special points in moduli space, you can make this scale lower, so you can include it consistently in the theory. What happens is that you have a superpotential, which includes fields of the type we're describing, fields that can be come from the vector bundle, so charged fields, where you have a function of complex structure and a potential mass term. Let me call it C plus C minus in the superpotential. The effect that you can find is that generally you have couplings in the superpotential which depend on complex structure. You can show that you can actually lift degrees of freedom. So when these mass terms are 0 as a function of complex structure, you have no constraints. And when you generate non-trivial mass terms, this will lift various combinations of matter fields and complex structure moduli in ways that I will say see notes. So to conclude, the things that I think are valuable from this lesson is that it is not actually a good exercise, either from the point of view of classification or from understanding the 4D physics, to ignore any pieces of your geometry. So this analysis that I'm describing of deformation spaces can be extended, as I said, to the Strominger system. So you can fluctuate full metric fluctuations as well as H. So Strominger, you can calculate the degrees of freedom coming from delta H, delta A, and delta G. And this is really the true moduli space of your theory. In general, this is much more rigid than you would have naively expected. So if you're in the business of engineering theories, of working on moduli stabilization, or understanding properties of that effective theory, you have to group everything together. This same type of analysis, so finding a new bundle-valued cohomology that you're calculating to calculate degrees of freedom, this can be done in type 2 theories. Type 2 theories as well. So not quite in this language, but very similar ideas. There's work by Martucci, Marchesano, and Gray, all of whom are trying to work out exactly the true moduli space of type 2 in the presence of various backgrounds. Again, this counting can be done effectively, and it can teach you something about the effective theory. So hopefully, the overall punchline of these lectures, even though I didn't get quite as far as I intended, the overall punchline that I hope you'll take away is that if you want to characterize effective theories, if you want to characterize dualities, if you want to be able to say, what are the possibilities, there are actual calculable things you can do that can try and bound this problem, make it finite, and you can work through to the properties of interest. So hopefully this is a little bit of a toolkit, and I wish you luck. You know. Yes. on the Calabi-Yau. Good. It's the rank of the adjoint of whatever gauge group you have. So if this was, an SU3 bundle, for example, this would be a rank 8. It would be valued in the 8 of SU3. Sorry? Yep, adjoint ranked. So that's exactly right. Yeah, where did I put this? So all of this as written, this is a sequence on X. And there's a non-trivial X that mixes the two. Yes. I mean, this is complex coefficients, and this, as written, is actually a one form valued over this space, which is different. I mean, everything in this problem is over Z. Okay. Yes. Dimensionally. I mean, these are cohomology groups over different spaces, but the dimension of the two is the same. So if you view this as this is a set of one forms that live over the total space here. If you work out the dimension of how many degrees of freedom is that, that is counted by the projection down to the base of this guy. Some other questions over here?
Just curious, if I want any construction for a pixel moduli, what is this?
Like, how far can you go with like moduli stabilization, or just? I mean, what is my goal with by state of the art? I guess I'm asking.
Those two requirements: pixel moduli, having something I can trust.
So in different types of string compactifications, the answer would be different. Let me answer it in heterotic, because that's the one that I have done the most with. We have, using all the tools that are available, just with Calabi-Yau backgrounds, using this kind of approach, we can get all the geometric moduli fixed up to one linear combination of the overall volume and the dilaton. And we've actually even found solutions where we had, in principle, no-go results against ADS vacua. So we could find Minkowski solutions that were almost stabilized, and we hoped that we could just bump them up a little bit and maybe find DS vacua. In practice, everything that we have of this type gave at least one runaway. So I know of in heterotic, there is no fully stabilized, getting absolutely everything, breaking supersymmetry vacuum yet. Okay, my personal opinion, actually even figuring out what the heck all your moduli are in F-theory is still a hard problem. I do not believe anybody who says that in F-theory they've got all moduli fixed yet, because we don't have that technology fully under control in F-theory, I would say. In type 2, for example, large volume scenarios, people have pushed this quite far. There's a lot of technology. Obviously, KKLT type approaches are also good. These have certain caveats or questions you might ask. Vafa gave you some examples of where some issues are. Personally, just from my point of view, I don't think there's any moduli stabilization scenario with supersymmetry breaking that is 100% compelling in string theory to date. I also am not unoptimistic that such a thing exists. I think we're finding more tools, and I'm hopeful that this is just a feature of our ignorance, not a no-go theorem. Vafa might disagree with me, but I feel like there's still hope that such things may be found, but we don't have them yet, would be my statement. I agree. Okay, great question. I am not personally working on this, but I happen to know that James Gray has a paper coming out in type 2 that will be out within a couple weeks, where he claims to have an analog of this for type 2. So that I believe is coming, but I know because we're in the same department, but I have not worked on that personally yet. So this guy up here? Sorry, a box. I'm sorry, I didn't understand the first word. Yes, absolutely. So if you just take where did this come from? That's a great question. I was sketchy about it. If you just take the long exact sequence in cohomology associated to this, it follows exactly from that. So. So I've been illustrating this for Collabio because it's easier to talk about. With collaborators James Gray and Eric Sharp, I can even give you the reference for this paper. We did the equivalent to this analysis for the Strominger system. So this has been completed for Heterotic in the Strominger system. There's also nice follow-up work that was done by Zinnia de la Osa and Eirik Spines, where they extended that. There's basically some very similar things that appear that involve generalized geometry. So instead of a tangent space to the total manifold, there's a generalized tangent space that appears. So this has been solved in Heterotic. For arbitrary flux vecua and other contexts pieces, I'm not sure that the complete story for all moduli has been worked out for arbitrary G structures in string theory, but there's pieces. So as I mentioned, the SU2 is coming, sorry, the type 2 theories are coming soon. Parts of it, yeah. There are, I should say there's some questions about, there's a lot of literature in generalized geometry. Mapping some of this into existing stuff in generalized geometry, there's still some open questions. But yes, we have the sequence formalism that you have exactly this, this cohomology of this bundle. And then we have some steps to interpret that in a generalized geometry context. There are still some open questions. But basically, the same analysis can be done and has been done in this context.
Can one be quantitative enough, as was mentioned, that to be in a regime where you can write actually the full bed potential? You can
Actually, yes, and this is something I'm extremely proud of. So the devil is always in the details. So the mathematics of this is the deformation object that you want to write down by Atiyah. This actually was worked out in math in the 1950s, so this is what you'd want to compute. And there were 0 examples in the math literature from the 50s until now of anyone actually doing this explicitly. So like, yeah, this is the thing you calculate, and no one had any idea how you calculate it. So actually, part of the hard work in this was figuring out explicitly how do you get numbers, an actual number, how do you write down the explicit form of that superpotential? And we do know how to do that for large classes of examples now. So that's something that we worked hard to just make computationally feasible in Heterotic.
combine that with the third sector, like standard model and together.
That's a great question. So this is saying, what Miriam has in mind is, can you combine this with model building? So if you want to build a theory that, in Heterotic, say, looks like the standard model, all these moduli, speak to all these different couplings. Can you actually fix yourself at a good-looking phenomenological regime in moduli space and actually calculate what you want? We've done various work towards that. So the nice thing in Heterotic is that you have 2 E8 gauge bundles. So you can actually do this sort of moduli fixing with one bundle and model building with the standard model, for example, with the other. And they're only gravitationally coupled. So in principle, you can do good things. We've gone a long way. There's still further work to go on that, I would say. So yeah, whether you can combine all the features you want into one manifold and get something that looks really sexy and actually stabilizes all your moduli and breaks supersymmetry and solves the cosmological constant. Not yet. Not yet.
So let's thank Lara for this wonderful set of lectures. And we convene for the last lecture today by Oliver in the afternoon.